Right, for a very brief introduction to the first part of topic two. Topic two is about measurement and measurement techniques. So, a few basic instruments that you should already have some idea about. Things like a meter rule, pretty basic, nothing really to be said there. Force meter, we might call it a spring balance, but really it can be calibrated to measure forces. Electronic balance or electronic scales, and protractor. So listen, no need to write anything in your notes about that, but that's simply just to state a few basic things that it's just assumed that you know how to use. All right, now when you use a rule, there's a couple of things, or when you take measurements, I should say, there are a couple of things that you need to watch out for. The first of these is what's known as parallax error. Now, parallax error involves the position or the angle at which you view things from. So if we've got on this scale down here, we've got something we're trying to read with a meter rule, and the meter rule's got some physical thickness to it. We must make sure that our eye is in position C, vertically above the scale. If we don't do that, then we would find that the scale lines up on an angle, and that lining up on an angle is what is known as parallax error. So you should have that simply the statement parallax error and this diagram then in your notes. Another thing to watch out for is something called zero error. The meter rules that we've got in the laboratories tend to have a little bit extra on the end of them so that the scale at the very end of the rule does not start at zero. That's what's known as zero error. So you need to make sure that you've got things lined up correctly so that you do not get zero error in your reading. So again, just take note of zero error and the diagram in your notes. We'll come back to zero error when we look at another measuring instrument a bit later, perhaps. Okay, two more precise measuring instruments. One of them is known as vernier calipers. Now, the word vernier refers to this scale here, which is known as a vernier scale, and it allows us to make a more precise reading. So vernier calipers are good for measurements at least of a few centimeters. You could go a bit more than that. You probably could go up to maybe about 10 centimeters. It is possible to measure the length of something, or if you're trying to measure, let's say, the inside diameter, you can use these inside jaws, where these jaws are placed inside something that you're trying to measure there. Now, vernier calipers are, in general, able to measure up to the nearest 0.1 of a millimeter. All right, so a meter rule could measure up to the nearest millimeter. Vernier calipers 10 times more precise. If you want to be even more precise, you can use something called a micrometer, or it's called a micrometer screw gauge. A micrometer screw gauge will measure up to the nearest 0.01 of a millimeter, 10 times more precise than vernier calipers. So in terms of your notes, diagram here, and this general note here. Okay, to go in your notes books. Right, so let's have a look in a little bit more detail how we use the scale on a vernier calipers to actually read things. So we're trying to measure the diameter here of that, so we put it in there. We look at the scale. We read from this, sorry, that's not quite lined up. We read from that point there, from the 0 mark. Now, if we have a look at that, this is 1 centimeter. That's 1.5. It looks to be about 1.7. Okay, so 1.7 centimeters. Now that would be to the nearest millimeter, but it should be possible then to actually figure out from that vernier scale what the next decimal place is. So let's have a look at that. Here's a more precise one for us actually to be able to, I think, see and take a reading from. So what does the vernier scale read? All right, so we come across 1 centimeter, 2 centimeters, we look at where that 0 is occurring. It's occurring somewhere between 2.6 and 2.7. All right, so the reading is 2.6 something. And then to get the next decimal place, we go across this scale here and we find which of those numbers best lines up with a scale division up above. And you'll find that they move from being, one side, and they get closer and closer and closer and closer. So I would say either 4 or 5 seems to line up quite nicely with the points up above. All right, so it's probably a 50-50 call as to which you go for there, either the 4 or the 5. So let's say 2.64 centimeters, or you could write it down as 26.4 millimeters. All right, so that's how we use vernier calipers, and you'll get a chance in class to practice reading those in reality. All right, the micrometer screw gauge, different sort of way of reading things there. Right, so let's have a look at that. I think those numbers at the bottom may be slightly incorrect. So how do we go about reading this? Okay, each of these divisions up here represent 1 millimeter. Okay, so we're going then 1, 2, 3, 4 millimeters. The divisions across the bottom represent the 0.5 millimeter in between. So this division here represents 0.5 millimeters. This division here represents 1.5 millimeters. The next one, 2.5, 3.5, etc. So on this particular scale, we can see that little mark down the bottom there. So therefore the reading is 4.5 millimeters plus a bit extra, and we have to decide what the bit extra is. So I'm going to actually write it down as 4.50, and then for the bit extra we use this scale here and we see where things best line up across here. All right, so using that scale, there's 10, 11, I'd say that's 12. So therefore the reading is 4.50 plus another 0.12, giving us 4.62. I think that's where we can see that there was wrong for whatever reason. It was actually meant to be a 2. So 4.62 millimeters. And again, you'll get a chance to practice using a micrometer screw gauge. All right, another instrument that you will need to become familiar with this year, at least in a little bit of detail, is something called the cathode ray oscilloscope, or CRO for short. It is something that's used for electricity. You can measure either AC or DC voltages with that. And what it does effectively is it displays electronic signals on a scale where on the vertical scale you've got voltage, and on the horizontal scale you've got time. And so you could have a signal like that or whatever shown on that cathode ray oscilloscope. So just take note of those couple of points about the CRO. There's a picture. You can put that in your books. Don't panic at this stage. It looks complicated. There are all sorts of dials and so on. We really just want to take just mental note of the fact that you're going to be using these, and later on when we study the topic of waves, we will actually get the cathode ray oscilloscopes out and we will use them to take measurements. Okay, so at the same time, at this point though, I think you can put that diagram though in your notes books. A couple of other little bits and pieces. You should know the difference between an analog scale and a digital scale. A digital scale is something then that has specific numbers like that, a digital stopwatch, and you can't read in between the figures. So that this watch reads to the nearest hundredth of a second here, but you can't read in between those hundredths of a second. So there is a set series of values that it can read, whereas an analog has got a needle or some sort of pointer that runs around, and that could theoretically stop at any position whatsoever, even though it might be quite difficult to read that scale. All right, let's just finish with this thing here, talking about significant figures. What's the length of the pencil? So the first thing we take note is that it's not reading from the 0 mark, it's reading there. So we might say that's on the 1 centimeter mark. And up this end here, it's on the 11 centimeter mark. So therefore, how would we write down the length? Would we write it down as 11 centimeters? Would we write it down as 11.0 centimeters? Would we write it down as 11.00 centimeters? You need to think about the scale that has been used and how precise the scale is. Now this is a rule that's been used. We take note that each of these divisions on that rule effectively measures to the nearest millimeter. So I would suggest to you that the most appropriate number of significant figures is that one there, 3 sig figs, effectively measuring to the nearest millimeter, because that is the precision of the scale that is being used. You could argue that you can measure to the nearest half a millimeter up there, and you could measure to the nearest half a millimeter up there, and so combining those 2 half millimeter uncertainties, then the overall uncertainty would be 1 millimeter, which is reflected by that being quoted as 11.0.